All right. Good morning, everyone. Welcome to G's PhD thesis defense. So G is a fifth-year PhD student from our group. He joined MIT in 2018. It's been 5 amazing years working with G. So he worked on a lot of amazing projects, have a lot of industry impact, like the temporal shift module was his first project. Even after 4 or 5 years, lots of projects on video standing is still citing his work, using his work. And later, he worked on the TinyML to deploy a lot these vision models onto microcontrollers from inference to training. It's 3 papers highlighted by MIT homepage, actually twice, which is pretty amazing to be able to run not only inference, but also training on a microcontroller that has only 256 kilobytes of memory, which is thanks to the algorithm and system co-design, which is pretty cool. And later, since early last year, he switched to large language models from TinyML to large ML. Lots of the principles can apply, and he has been working on the large language model quantization and efficient inference to bring down the serving cost of large language model from 16-bit to 8-bit and then to 4-bit. Lots of his work, like SmoothQuant AWQ, has been widely integrated by the industry, like NVIDIA FasterTranformer, NVIDIA TensorRT-LLM, Intel, and also many other open source community like vLLM and etc. So without further introduction, let's welcome G to give the presentation.
Yeah, thanks so much for Professor Han for the kind introduction and all the kind words. And also thanks for everyone attending here today, no matter it's physically in the room or over the Zoom. So I'm glad here to share some of the work I have been doing during my PhD study. So the title of the thesis is Efficient Deep Learning Computing from TinyML to Large Language Models. So let's get started and jump into a bit of the background. So over the years, deep learning model has continued to scale with the increasing large model sizes and computing capabilities, enabling various remarkable performance, especially in the age of large language models and generative AI. So here we plot a figure of the model size growth over the years for various large language models. So please note that the y-axis is actually in log scale. So it's very clear that the model size has been growing exponentially over the years without a trend to slowing down.
G, can you hear me?
Yes.
G, I'm sorry to interrupt you, but you share your slides on Zoom.
Oh, sorry. Yeah.
Awesome.
Okay, sorry about that.
Don't worry.
Let me see. Yeah, let's get to the presentation. Okay, so as we mentioned, the model size is growing exponentially over the years, but the problem is that the hardware growth have failed to follow up. So here we also plot the memory size of different hardware accelerators, including GPUs or TPUs, that growth over the years. And it's clear to see that the GPU growth, the hardware growth speed is falling behind for the model size growth. And this situation is actually even getting worse as the Moore's law is slowing down recent years. So we cannot just rely on domain-specific accelerators to help us address the problem. We need efficient techniques to help us bridge the gap between the supply and the consumer of the compute. So this is actually getting even worse and quite essential as in the age of large language models. So even the largest player in the field, like OpenAI, has been failed to serve the increasing demand from the customers. So this screenshot was taken at the earlier of this year when they just launched GPT-4. So a lot of people are trying to upgrade to ChatGPT Plus so that I can use the model, but their server has failed to scale up and accommodate more users. And things get a little bit better later, but actually until last week, it has not been solved. And with the launch of the new GPT features, they again have to stop the subscription or the upgrade service because of the hardware shortage. So therefore, we think that efficiency is a key component in the age of deep learning computing, especially nowadays. So I have been working on various techniques over my PhD study to improve the efficiency of deep learning computing. So I have been working on like two extremes of scaling. So deep learning traditionally, like starting from AlexNet, has mostly been running on single GPUs. And one scaling trend is to scale up the model such that we can build super large foundation models, run on multiple GPU nodes or even multiple data centers. So in this trend, I've been building efficient methods for large language models, including quantization and working with colleagues on some of the system optimizations. And the other very end of the scaling is actually to squeeze down the model size so that it can fit smaller or edge hardware devices like smartphones or even microcontroller units. So during the study, we find that it's actually quite essential if you want to co-design both the algorithms and the hardwares or the systems to provide the best performance. So for the algorithm side, we propose more methods for both training and inference stage of the deep learning computing. And for systems, we also develop corresponding solutions for both inference and training. So we studied both general techniques, for example, like pruning, quantization, or architectural design, which can be applied to various deep learning models. And on the other hand, we also explore domain-specific optimization opportunities, including like video recognition or image generation. So that's the overview of this talk. We will start with our recent work on large language model side, and then we'll go over to other dimensions as well. So let's start with efficient large language models, where we explore different post-training quantization methods, and we develop TinyChat for efficient serving. And I also will shortly introduce our recent work on improving the multimodal large language models. So as a start, we can introduce a bit about quantization. So quantization is a method to represent a floating point number with low bit precisions. For example, something like 4-bit or 8 bits. So if you quantize a model for it can reduce the hardware requirement to serve the model. So here is an example of the GPT-3 175 billion parameter model. It's a relatively old model, maybe 3 or 4 years ago, but it's still quite hard to fit in a single GPU device. So if you try to deploy the model with IP16, which is basically the default choice people use for running large language models, each number or each parameter requires 2 bytes. Then for a 175 billion model, you require at least 350 gigabytes of memory to just hold the model. So it corresponds to at least 5 A100 GPUs with 80 gigabytes of memory each. And on the other hand, if we can quantize model with int8, then we can instantly reduce the GPU memory by half. So now we only require 3 GPUs for the inference. So in this section, we mainly explore post-training quantization schemes for large language models, because these models are usually super large and expensive to train. So if we can develop post-training method, it will allow us to quantize this model without a crazy hardware requirement, and also it will lead to better generalization. So we don't need to worry about a data mixture. So we have two quantization schemes. One is SmoothQuant for 8-bit wait and activation quantization, or short for W888, for batch inference, where it is usually compute bounded. And we also develop AWQ, which is for low-bit wait only quantization. For example, it only quantizes weight into 4-bit, which is good for memory bounded cases, like running with a smaller batch size. So let's first delve into SmoothQuant. 8-bit int8 quantization has been the industry standard if people want to deploy a convolutional neural network on edge devices like smartphones. So people usually always quantize model into 8 bits so that it can run faster on the edge device. But the problem is that people have not been able to use it for large language models for a long time over the years. So why is that? So actually, if you apply 8-bit quantization for both wait and activation to large language model, So as the model size gets larger, it will actually suffer from a super large performance degradation. So here we provide a figure comparing the accuracy for the floating point 16 serving, which is in green, and also the quantized serving, which is in yellow. So for the floating point number, as expected, as the model size gets larger, the accuracy continues to get higher, which is just one of the advantage you can get from scaling. But on the other hand, if you quantize model, then as the model size grows larger above some threshold, like 7 billion parameters, we are suffering from a huge accuracy degradation. So
wait, what task is accuracy being measured on here?
I think this is the lambda data sets.
Okay.
So actually we are observing a similar trend, but this is just one data set we use for illustration. Yes.
Can you explain why, like, I mean, it seems remarkable that there's like no degradation at the beginning and then you get this incredibly rapid drop off and then it sort of stabilizes the amount of drop off. Like,
Yeah.
can you give some intuition about why it's behaving this way?
Yeah, so we'll go into the reasons why it fails in the next slides. And the reason why it's kind of saturates for the degradation is that it's getting a random accuracy, so it cannot get worse compared to random. So there's a lower bound. Yeah. So yeah, a good question. So we actually find that this kind of the accuracy degradation is due to the systematic outliers that emerge in the activation. So which is also coherent with the previous literature. So to verify the idea, we plot the distribution of weight and activation of large language model, specifically OPT 175 billion parameter here. So we have some interesting observations. Firstly, the weight distribution is super flat, which means that if you the y-axis is the magnitude of the weight. So the weight is super flat and centered around 0, so within a super narrow range, which means that this kind of distribution is actually kind of very easy to quantize because they fall in a restricted range. While on the other hand, for the activation on the left-hand side, we are seeing a lot of the large outliers, which is denoted in red. So if you take a closer look, the y-axis is actually truncated. So these outliers are actually larger than it looks in this figure. So this kind of the large outlier will stretch the range of quantization. So basically doing quantization, you want to improve the mean and max range. So for most of the non-outlier values in blue, they will be pushed to around 0, leading to a large quantization error. But one good property or one lucky thing we have is that these outliers are actually quite persistent. By persistency, we mean that if for a certain channel, if there's an outlier for a certain sample, then it's most likely to be always an outlier or always super large. So if you look at the other two dimensions, one is the channel dimension and the other is the token dimension. Token dimension basically means different samples. So for each of the outlier channels, it's usually always large across different samples. Of course, there are some exceptions like those in lighter blues, but for generally this kind of behavior applies. So this kind of persistency gives us a chance to perform a fixed transformation to help us get rid of the outlier issues. So a very intuitive thing we can do is that we can simply multiply 0.1 to one of the outlier channel in the activation, and then we multiply 10 to the corresponding channel in the weights. And because matrix multiplication for weight and activation is a linear transform, so if you multiply 0.1 to one side and 10 to the other side, then we are actually getting still the mathematically equivalent outputs. But with this kind of transform, we are actually suppressing the outliers in activation by multiplying a very small number. So as you can see, after this kind of transform, the outliers originally in the activation are flattened out by a lot. And at the same time, because we multiply a large number to the weights, then we introduce some of the outliers in the weights. But because originally the weight is super easy to quantize, so even by introducing some of the difficulty, it still can be safely quantizing A bits. So essentially, we are trying to migrate part of the quantization difficulty from activation to weights, so that both of them can be safely quantizing A bits. So here we also provide a example. This is completely made up examples. So just to better illustrate how things is doing here. So of course, actually the outlier is much larger than something like 16. But basically, we're providing a sample of activation weights with 4 channels. So we calculate a specific scaling factor here. And by dividing the activation or X with the scaling factor and multiplying the weight with the scaling factor, we are still getting the same outputs after matrix multiplication, but now the dynamic range for each channel is reduced. So the question is, how do we choose the optimal scaling factor? So here we rely on a simple heuristic that because we are quantizing both the weight and activation with the same 8-bit quantizer, we actually want to make them roughly equally hard or easy to quantize. So we simply take the square root of the per channel maximum value for activation and weights, such that after the transformation, they have the same maximum value for each channel. And of course, like this is basically the algorithm side of our SmoothQuant, because we are smoothing out the outliers, so that's why we get this naming. But on the other hand, if you want to get some real hardware accelerations, for example, like if you want to make it run fast on GPUs, we still need some efficient system implementations. So here is a diagram of a typical transformer block that we studied for OPT models. So here there are some arrows for activation and some like squares for weights. So we are quantizing all the like compute intensive operations, including linear layers and also batch matrix multiplications for attention into 8 bits, while preserving the layer norm and also the residual connection in IP16, because they are generally light in computation while also essential for performance. So here we show some like accuracy and efficiency results of large language models with our SmoothQuant. So remember this graph we introduced before, where we suffer from a large accuracy degradation with 8 bits, but with our SmoothQuant method, we are actually able to match the accuracy of the IP16 model while still using 8-bit quantization. And here are some like hardware statistics, both on the accuracy and also on the latency. So on the right-hand side is the, both on the latency and also the memory usage. So on the right-hand side is the memory usage of the comparing IP16 and our SmoothQuant with 8 bits. So it's kind of straightforward to see that our method can reduce the GPU memory usage by roughly half, because we reduce the bits by roughly half. But with the reduced memory, now we can serve the 175 billion model with only 4 GPUs instead of 8 GPUs. While at the same time, when we look at the latency is actually faster compared to IP16 with 8 GPUs. So essentially, we are reducing the hardware cost by half without like slowing down the inference. And this like study is done earlier last year before the Llama models. So for most of the study, we're looking at something like OPT or Bloom, but definitely Llama model is a new standard for open source large language models. So later we also apply our method to Llama models, and we're getting some like a pretty good perplexity. So there's still a little bit gap, but it's generally like smaller than 0.05. So we think we can also safely quantize Llama without hurting its performance. Okay, so this concludes the first work, SmoothQuant. So we introduced algorithm and system implementation to reduce the cost of batch serving for large language models. So SmoothQuant is especially designed for a large batch serving, for example, like batch size 128. Here is a loop-like model. If you are not very familiar with that, basically this diagram tells us that you need to get a high compute intensity so that you can utilize the compute capacity of the hardware, like GPU. So if you can run with a large batch size like 128, then you get to reuse the weights over multiple samples. So in that case, you can get a high compute intensity. But sometimes we also want to run large language models on local devices. For example, you may want to run a private coding LLM on your laptop so that it can help you do code completion. So in this case, we're basically serving an inference with a batch size of 1. So which leads to a low compute intensity and low flops utilization. So for this kind of workload, we actually need low bit weight only quantization. For example, like W4A16, which means that we're quantizing the weights into 4 bits which is even half, like twice smaller compared to 8 bits, so that we can reduce the memory we need, memory bandwidth, and improve the inference efficiency. So this is why we go on and develop AWQ, which is short for activation aware weight quantization. So in this work, we are targeting low bit weight only quantization in a group-wise format. So by low bit, we are targeting like 3 or 4 bits. And by group weight only, it means that we only quantize the weights, but during the computation, we still upcast the weights into IP16 for inference. because this kind of workload is mostly memory bounded, so but not compute bounded. And for group-wise, it means that we're taking a kind of quantization formulas that share the scaling factor for every, for example, 64, 128 numbers. So it's a more fine-grained formula compared to per channel quantization or per tensor quantization. So in the previous study from University of Washington, people have found that this kind of formula gives us a better trade-off in terms of model size and accuracy. So this kind of low bit quantization is good, but if you simply do round to nearest for the low bit quantization, you're actually suffering from super large accuracy degradation. So here on the figure on the right-hand side, we're comparing IP16 perplexity and also round to nearest perplexity. So if you are familiar with NLP, you see this number, you are immediately understand the model is actually just broken, so it doesn't behave anything like as you expected. But luckily, we find not all the weights are equally important. So if you preserve only 0.01% of the salient weight channels in IP16, like for illustration, we preserve the second row in IP16 on the figure on the left. So if you simply preserve the 0.1% channel in IP16, we are getting an immediately improvement in terms of perplexity, which means that we are saving the model's performance by a lot. But the question is, how do we figure out which channels are salient and what kind of channels to put in IP16? And one interesting, one like old implemented, like traditional study is that people usually, in the field of model pruning, people usually believe that the magnitude of the weights is a good metric to indicate its importance. But we find the interesting behavior, actually the activation magnitude determines the saliency of the weight channels. So on the right-hand side, if you keep the 0.1% channels in IP16, according to activation magnitude, you're getting a big improvement. But if you're sorting it based on weight magnitude, it's almost similar as random, where the improvement is negligible. So we believe this is because this activation channels with a large magnitude corresponds to more important features. So if you keep the corresponding weights in IP16, you can better protect those features. Yeah, but this is all good. But the problem is that we're still stuck at a mixed precision solution, even though the overall number of bits is not that large because it's only 0.1%. But this kind of mixed precision workload is very bad for system implementation or speed up. So we are basically getting only 25% speed up if we are falling in this kind of mixed precision paradigm. So the question is, how can we protect these salient channels without introducing mixed precisions? So here is some math that we put into analysis for the quantization process. But I think due to the time limits, maybe we don't have time to go over it. But basically, one interesting thing we find is that if you simply scale up of the salient channels by a number, for example, like by 2, multiplied with the second channel before quantization, and of course, similar to SmoothQuant, you need to inversely scale the activation so that the output does not change. But simply by scaling the salient channels up, we can reduce their quantization error. As we show on the right-hand side, if you scale it by 1.5 or 2 or 4, they are already getting perplexity smaller than 15. If you just do round to nearest, it's something like 40. And this is all, but it's also a bit tricky to find an optimal scaling factor for each channels. So we fall to an automated search method where we aim to minimize the quantization error from the quantized output and also the floating point outputs. And because the quantization function is not differentiable, so we design a search space here using a grid search. So essentially, Sx is the scale of activation, and alpha is just a number between 0 to 1. So we use grid search to find the optimal scaling factor for each layer to minimize the quantization error. So there are a couple of good properties or advantages of AWQ method. Firstly, it's accurate and easy to implement. So here we compare our method in perplexity compared with the state-of-the-art method GPT-Q previously, and we are getting a consistent improvement in the Llama model's perplexity. But there's also another less obvious advantage of AWQ, because methods like GPT-Q, they requires a calibration set to perform a regression or reconstruction based on mean square error methods. Based on a specific calibration set. So it's actually easier to overfit the calibration set, while our method basically observes the overall activation magnitude. So it usually has better generalization. So to verify the idea, we perform some ablation study. On the left-hand side, we are looking at the perplexity number versus the calibration set size. So our GPTQ, our AWQ method requires a much smaller calibration set to get a good perplexity. And on the right-hand side, we are taking two subsets from the PIO data sets. One is a medical data set called PubMed, and the other is an email data set called ANRED. So they have very different distributions. So if you perform quantization, calibration, and evaluation on the same data sets, both methods works the best in terms of perplexity under this setting. But if you simply change the calibration set and the evaluation set, for GPTQ, we are suffering from a 2 to 5 perplexity increase, while for our method, the gap is only like 0.5. So I believe this kind of robustness to the calibration set distribution is actually quite important for generalist foundation models, because you expect the model to behave well on all kinds of downstream distributions instead of just some like holdout tasks. So thanks to the generalization, we can apply our method, AWQ method, to address a large language model with various applications. For example, this is the code llama models. So with 4-bit quantization, we're actually matching the accuracy of the IP16 model on this coding data set. And we are outperforming the GPTQ method so that we are able to run these small models on your laptop for some coding assistance. And for the first time, also try applying our method to some multimodal foundation models. This is Open Flamingo, which is a like reproduction of the Flamingo model from DeepMind. So this is the metrics for captioning on the COCO data sets is higher the better. So if you apply round to nearest quantization, then there will be a large gap in terms of the like CIDR score drop, while our method is able to close more than 75% of the error. So here are some samples. Like for example, in the first sample, if you use round to nearest quantization, the model will give some like nonsense caption, like the model airplane flying in the sky, while with our method, you can still see it's sitting on a grass field. Another example is the multimodal LLMs for Lava, which can do visual reasoning. So here is a Mimi, and if you do round to nearest, if you ask the model to perform Mimi explanation, the round to nearest method will hallucinate, saying that there is some picture of planets placed on top of the food. While our method, with our method, the model can still get this is a humorous take on the concept of looking at picture of the Earth from the space. So here are just some like results for the AWQ method. And similarly, like as SmoothQuant, we also need to build an efficient system so we can convert the theoretical savings into realistic speed up. So this is a TinyChat work done with my lab mates. So there are two kinds of surfing info. One is like FasterTranformer from NVIDIA, which is high performant, but they are also kind of hard to use. While HuggingFace excel at the usability, but the efficiency is actually quite low. So TinyChat aims to bridge the gap between the two dimensions, providing an efficient, lightweight, and Pythonic solution. So we think the Pythonic native nature is very important because it allows us to compose our tech stack with other solutions, for example, like vLLM, so that we can combine all these great features together. So with the system support, we are able to speed up the generation on 4090 GPUs by about 3.3 times for 4-bit quantization. So this Llama 7B model can run now at 166 tokens per second, which is super fast. And now, apart from the cloud, we can actually also enable some edge LLM deployment. So this is an edge GPU device from NVIDIA called Orin Nano. So with our method, we are able to get 30 tokens per second generation. So we believe the low-bit quantization is even more important for these edge GPU devices because they have limited memory bandwidth, something like 200 gigabytes per second, while the desktop GPUs usually have something like 1 terabyte or 2 terabytes per second. So to sum up, our work has been widely used by like industry partners. For example, like our work has been used by NVIDIA, has been integrated into NVIDIA's FasterTranformer and TensorRT-LLM, which are basically the industry standard for large language model serving. And we all Intel also use our method in their Neural Compressor and QA so that they can efficiently run those quantized models on CPUs. And we also work with the open source community like Berkeley on their vLLM surfing and the FastChat project. And our method is also getting to the HuggingFace Transformer and text generation inference, which is another popular tech stack for efficient surfing. So apart from the quantization study, like this summer, I've been also work a little bit on the multimodal large language model side, because during our previous study, we generally find that the open source large language model has a, for the multimodal settings, have a limited performance, is falling much far behind from the GPT-4b solution. So we believe that this is because it lacks a thorough study of the pre-training process, because people generally just simply focus on instruction tuning process of these models. So for a little bit background, for multimodal large language models, we're basically trying to augment the large language model with visual inputs. So basically, we simply encode the image with some like visual encoder like VITs, and then concat the tokens with textual tokens and feed to the large language models. So we have several interesting findings, and we don't have time to go into details, but basically we find that the data types, and one thing is that it's very important to fine-tune the entire large language model to allow the like deeper layer embeddings to align between modalities, and also like we need some kind of interleave data blend for pre-training, and also joint supervised fine-tuning to get the best performance. But with our study, we're able to consistently outperform the previous state of the art on 11 out of 12 benchmarks, thanks to the better pre-training under head-to-head comparison. And the pre-training also unlocks a lot of the interesting capabilities. For example, during instruction tuning, the model only sees a single image, but because of the good pre-training, it can actually reason above multiple images. For example, this is an example from the flamingo paper, where our model gets the all these photos are for flamingos, but they have different art styles. The model can also do in context learning. It has been a very important topic for the flamingo, but not a flamingo paper, but not the open source implementations. But with the in-context learning, we basically can put the image and text pairs into the context and ask the model to generate some text accompany the last image. So we've been doing this for OCR tasks or math reasoning tasks. And the third example is actually a bit more tricky. Basically, we are providing a landmark of a certain country, and the model needs to predict the food famous for this country. So it's essentially multi-hop reasoning, but our model can also get this correct. And because of the large pre-trained corpus, we find our model and also can aid self-driving development by reasoning for some corner cases. Like this one is not quite usually not something you'll see day to day when you drive, but basically the model can learn that there's a chair flying out of the back of the truck, and you should actually pull over if you see something like this. So it's a good lesson we can take. Okay, so this concludes the part on the scaling up side. So on the very other end of scaling is how we want to compress model and scaling down into edge tiny devices like smartphones or even microcontrollers. So so this is an area we term as TinyML. So like on the very end of the other end of the scaling up for foundation models, people have also been trying very hard to squeeze the model and deploy them on low cost or low power devices. People have been trying to squeeze the model from cloud AI into the smartphones to enable mobile AI. But IoT devices is the next step for scaling down. And this people have billions of devices everywhere, like for example, in your refrigerator or even in a calculator. So if we can enable AI on this kind of small hardware, we are going to enable a lot of AI applications. But the problem is that this kind of hardware usually has a really tight memory constraints. So cloud and mobile AI usually have gigabytes of memory, but the tiny AI devices usually only have hundreds of kilobytes of memories. So it's like 5 orders of magnitude smaller compared to the GPUs. So due to the limited hardware capacity, people have been only able to do some toy applications. For example, this is a demo from Google. They use this microcontroller to classify 3 fruits, mostly by looking at the color. So this is definitely not something we want to stop at. So our work at MCUNet aims to bridge the gap and enable real-life applications of deep learning on this tiny hardware. So it's very interesting that despite the large language model and TinyML have a super dramatic difference in terms of scale, they are actually facing the very similar phenomenon where the model size has outgrown the hardware capacity. So actually we can share a lot of the efficiency optimization techniques. So let's get into my first work in this area, which is MCUNet, basically the system algorithm co-design method to enable ImageNet level deep learning on microcontrollers. So there's a lot of existing work for efficient inference. One part is to fit optimized model architecture, either with manual design or with like architectural, like neural architecture search in the auto ML math way. The other part is people are also trying to optimize the library given a fixed deep learning model, something like TVM for scheduling optimization. But we find that both of them are not enough in TinyML with really constrained hardware capacities. So we need to co-design both the algorithm or the model and also the inference library to provide the best efficiency and accuracy trade-off. So our MCUNet consists of two parts. One is TinyNav, which designs the efficient neural architecture, and the other is TinyEngine, which provides an efficient compiler or runtime. So both of them are optimizing the same loop with AutoML to get the best performance. So co-design the system algorithm gives us a lot of advantage. One thing is definitely that the co-design brings the best performance. So here is the ImageNet top one accuracy when we try to run feed a model within a 300 kilobytes microcontroller. So if you simply optimize only the system or the model, you're of course getting better accuracy compared to baseline. But if the co-design still offers the best accuracy up to 62%, which is almost 23% higher than the solution in the first row from Google. And actually, our solution is the first to achieve a milestone ImageNet accuracy like 70% on commercial microcontrollers. So compared to the same hardware compared to a previous solution, we are getting 17% accuracy improvement. We think this is an important milestone because just like VGG in the age of GPU computing and also the mobile net in smartphone deep learning. So another advantage is that the co-design actually expands the design space and allows us to explore some of the optimization opportunities that is not available if you simply look at the single side of the optimizations. So here we look at, we take a case study and we look at the usage of MobileNet V2, which is the efficient edge deep learning model, and we check the memory usage of each block as the network goes deeper. So we can see a very imbalanced distribution. So on the left-hand side, there are first 5 blocks uses a large memory. So if you run a model, you want to feed the model within the peak memory within your hardware. So due to the first 5 layers, you need something like 1.3 megabytes to run this model. This is because you are running the model layer by layer, and the resolution of the initial stage of model is usually high. So it leads to a large feature map size. So on the right-hand side, if you want to run a 2-layer convolution, when you run it layer by layer, you need to feed both the input and output activation in the memory. So that leads to the high peak memory on the left-hand side. But if we can enable a new inference scheduling, for example, like a patch by patch scaling, so basically we don't run the entire feature map, but instead we only run a small patch at a time. So by enable patch-based inference for the first 5 blocks, we can significantly cut down the memory usage of these layers. And by overall peak memory also can be reduced by 8 times. So this is an opportunity if you cannot explore if you simply look at the model and the system. And this kind of the system optimization also allow us to build a model with a higher resolution inputs so that it can enable other vision applications like object detection. So with this kind of co-design and patch-based inference, we are now able to get better accuracy at 4x smaller peak memory. And interestingly, we are able to get over 90% VWW accuracy, which is a very important TinyML benchmark with only 30 kilobytes of memory, which is like quite small even for IoT devices. And here's like some demos we've been building, running like object detection, either for face and person detection on this IoT or microcontroller units. So on the right-hand side is the AirPods case. So the screen actually takes a lot of the space. So if you simply look at hardware, it's even smaller, and it can be powered by some like phantom battery. So we have talked a lot about the optimization on the inference side. So can we further enable learning on the edge? So different users have different data distributions. For example, people have different accents, and you sometimes hope that your like intelligent device can adapt to your custom data, but without uploading to the cloud, which will lead to higher costs and some privacy issues. So in our later work on device training under 256 kilobytes of memory, we further propose some techniques to enable inference, for on-device training of under TinyML setting. So it consists of 3 techniques. One is quantization over scaling, which allows us to directly update the quantized model. And second is sparse update. Basically, we want to update only the important weights for transfer learning. And thirdly, we implement tiny training engine, which allows us to, is a compiler that allows us to achieve a good memory saving with all this from the algorithm side. So overall, we are able to achieve over 1,000 times memory reduction compared to the PyTorch solution and fit everything under only 256 kilobytes of memory. So maybe we can get a little details into the second technique, which is sparse update, because we find this is actually quite interesting. We can apply it both for tiny convolution neural nets as in our work and also even to large transformers. So the basic idea here we try to do for sparse training is to figure out which layer or which part of the weights are important for transfer learning. And we only want to update the weights that has a high contribution to the transfer learning. So we are getting some like very different patterns for MobileNet V2 and transformers. So basically the first point-wise layer in MobileNet V2 is important for transfer learning, and also the QKV projection and the first FF1 layer. While the other layers actually, if you update them, that doesn't contribute to the transfer learning accurate flexibility. Okay, so that concludes the part of my work on the TinyML era. So our work has like for microcontroller, TinyML has been widely covered by different media, including MIT News and Wired and MIT Tech Review. So people are like also IBM is working with us to deploy these techniques into more applications for edge devices. Now let's go to the last chapter. I think I'm maybe getting a little bit slow, but the last chapter is about domain-specific optimizations. So in the previous two chapters of discussion, no matter it's large language models or TinyML, we are focusing on general techniques like pruning or quantization or neural architecture search that can be applied to various applications. For example, like for vision, you can do it for classification, you can do it for detection, and for language, you can just apply to the transformer for all kinds of tasks. But sometimes if you take a closer look at your application, you can explore some like domain-specific optimization opportunities. Here we briefly introduce two of Chris' work. One is for video recognition, the other for image generation or editing. So a little bit of the background. Video is a very important data that is super large in terms of size, and it's important, but it's very costly to process. For example, YouTube every day has about 10 to the 5th order of hours of videos uploaded, and you need to process it for recommendation or classification. And even for the edge cases, like for example, in a hospital, perhaps want to do video analysis so that you can monitor if the patient is falling into a ground or something. So it's important for both cloud and edge. Traditionally, there are multiple ways to do video recognition. One is using 2D CNNs applied to each of the frame, treating as a sequence of image, but they cannot do the temporal modeling. So more natural ways to simply use 3D convolution neural network, which can jointly model spatial temporal features. But the problem is that it's quite expensive. So a 3x3x3 convolution kernel consumes 3 times more compute and parameters compared to a 3x3 2D convolution kernels. So as an alternative, we propose TSM, which is short for temporal shift module, an efficient module that has different 0 flops and 0 parameters, and it can enable temporal modeling. So the basic idea is that as shown on the upper side. So originally, the original tensor for each row, it only has one color, meaning it has information from one specific type stem. But what we do is simply to shift parts of the features along the temporal dimension to exchange information from the neighboring frames. So it's simply a drag shift. And this is for offline processing. You can do bi-directional processing. And on the right-hand side, sometimes you are doing online video recognition. You can also shift from history to past to future. So simply insert this module within 2D convolution networks, and everything is still running in 2D while we can enable temporal information exchange. So compared to the previous work, like 3D CNNs like i3D, we are getting a better accuracy and flops trade-off. And actually, we are able to, it's actually quite edge friendly. We are able to do some online gesture recognition on simply a $99 JSON Nano with only running at 70 FPS for some like gesture control applications. So despite the work was done back in 2019, and actually one of the survey that people did this year, earlier this year around the summer, they find that our model actually, our method is actually getting quite good performance when equipped with the state-of-the-art conv backbone, something like ConvNext. So we're actually outperforming a lot of the recent transformer-based methods given in this study. And our model, due to the design, is actually also quite scalable. So back in 2019, we also experienced scaling up the training of the large video networks. So nowadays, people are using like thousands of GPU for foundation model training. But at that time, this is also a kind of early extent. So we are able to scale up the training to over 1,500 GPUs on the Summit supercomputer and getting a pretty good scaling behavior and finish the training of the largest video data set kinetics in only 15 minutes without any hurt in terms of the accuracy. So here is another like quick demo for using TSM for to aid video detection. So on the left-hand side is the per frame detection results. Everything works as normal. But if you shift the car's headlights towards camera, you get some misclassification. Like for example, it says there's a train because of the glares. Well, with our method, we're able to aid the detection by getting rid of this weird wrong predictions with the aid of temporal information without any actual cost in terms of the latency. So another application we're looking at is image generation or image editing. So nowadays people are using diffusion models a lot, but back in 2019, GAN model is definitely the state-of-the-art method. So basically, the GAN model takes in an input vector, it can generate a specific image. And one way people use GAN for image editing is simply first project the existing image into the latent space of a GAN model, such that the GAN generator, when take this latent code, can generate a similar image as the original image as input. Then we manipulate this latent code with some pre-computed directions. For example, some direction makes the people smile, and some direction make the people's hair whiter. But the problem is that the inference of the generators is also quite slow. So if you are doing some like iterative refinement, then it's going to be quite laggy and hindering interactive user experience. So during my internship at Adobe, we proposed AnyCost GAN, which we were trying to build a single unified generator that can be run at different quality and efficiency trade-off. So we take the inspiration from the rendering pipeline. So during the editing, we run the model in a fast, low-cost mode to provide a fast preview. While when we finalize the editing, during the idle time, we can run the full model to get a higher quality outputs. So the important thing is that the different models, like at different capacity, they have the consistent output, so we can use it as a good preview. Basically, we are training any AnyCost GAN model that can run at diverse resolutions and model capacities, specifically by different channel numbers. So when we run the full model, it has a high resolution and high capacity. And for the smallest model, we're running at a reduced capacity and reduced model size. So here is some like visualization we make when we train the model to on FFHQ data set. So at different resolutions on the x-axis and different channel numbers on the vertical axis. So from the upper left to the lower right, we are seeing 100 times of compute in terms of the 100 times gap in terms of compute, but they are still providing like visually similar outputs. And here is a demo. I'm not sure whether we have time to play over it, but basically the thing is that the more like people can use it for editing, but this is super slow. So we can actually enable a faster preview by changing the channel and resolution. Maybe we can go back to this later, given we are a little bit delayed. So of course, like GAN models is like kind of in the history right now. So diffusion model kind of take over. But with the talk with my colleagues at Adobe, they're actually extending this method to help scale up the deployment of their latest Firefly service to improve the efficiency. And for our work on video and AnyCost GAN, we also get some like media coverage. And interestingly, our work has also been used by other people. For example, DeepMind is using the TSM module for unsupervised learning because it has a good learning efficiency. So they can use our model to get a better unsupervised accuracy. And also University of Washington is using our method for contactless vital measurement during the outbreak of COVID. So that concludes all the research I'd like to share today. So in summary, during my PhD study, I've been fortunate to work with a lot of people on various interesting projects. So our work has get about 8,000 citations and 9,000 GitHub stars. And I also participate in the teaching assistant this year, like for the TinyML course. And we are getting a lot of good community feedbacks. We are getting about 40K, 24K views on the YouTube, and also about 800 members in the Discord channels. And this is just some of the screenshots we take from the midterm study. So generally people think we are getting a good lecture note and a very good lab design. So for summary, during my PhD study, I've been working on a full stack design for efficient deep learning computing. So it covers different stages from inference to training, different techniques, including pruning, sparsity, quantization, and architectural designs. It covers different stacks from the algorithm and system, and also at very extreme scales like large language models or TinyML. So for work on the large language model, quantization inference is mostly about the inference with quantization and also co-design the algorithm system. And for the TinyML inference work, it's mostly about quantization and architectural design, while for the TinyML training work, we introduce sparsity to improve the training efficiency. Finally, for domain-specific application, we explore novel architectural designs that allow us to improve the efficiency of these specific applications. So looking forward, we still believe that efficiency is the key as the deep learning develops into the future. So the compute paradigm has shifted a lot over the years. So people originally has been mostly using on PC, and the last paradigm shift is the mobile first era, where people basically just move everything to the your smartphones. And recently, like with the development of these foundational models, people are actually redo everything and rebuild every application with the aid of AI. So we are actually witnessing an AI first era. Like for example, people are even arguing you should use AI for operating systems. So this foundation model-based application will be ubiquitous, like from like for example coding completion to translation and to image generation or even AI-assisted search engines. So the full stack optimization is a key to improve the efficiency of and democratize those AI applications. So we need to co-design with hardware system and algorithm to provide the best efficiency. And lastly, as the recent development, we think that data is also another very key component to allow us to get the best performance out of a small model on specific hardware devices, which we didn't get a chance to explore in this study. Finally, I would like to take this chance to thank a lot of the people I've been working with, like advisors, collaborators, and my friends over the 5 years of journey. So firstly, I would like to sincerely thank all the committee members, Professor Sung Han, Professor Vijay Reddy, and Professor Jacob Andres for coming into the defense. So Professor Sung Han is the best advisor I can ever imagine. So I've been working with him for more than 5 years, starting from my undergraduate study. So he gave me a lot of support and help during my gap year, where I was kind of lost and a little bit, wondering like what to do for the future. So I still remember I slept on his couch in the Bay Area apartment for a few days during my visit back in 2018. So ever since I started working with him, he has been taught me a lot about how to do impactful research, and even on some like other dimensions like startup. So he always provides the best support for us and help us pursue our research interests. So he is not only the academic advisor, but also my life advisor that I always look up to. So I also like to thank a lot of my lab mates during at MIT Hard Lab and also alumni. So the list is a little bit too long, so I probably am not iterate. But it's fortunate to work with such a bunch of amazing people, so we can build some cool things and stuff together. So outside of our lab, we also have a lot of friends at MIT that I not only like talk, maybe I didn't talk anything about academic with them, or maybe a little, but mostly we had a lot of fun as friends. And also I'd like to thank a lot of collaborators from the industry and other schools. For example, like Chuan and John from MIT IBM Boston Lab, and also a lot of collaborators from Stanford and Berkeley, including Li Jia, Chen Lin, Stefano, and Fan Chen. And also I'd like to thank my undergraduate advisors, for example, at Tsinghua University, for example, Professor Wang Yu, who has led me into the field of efficient deep learning, and Professor Ji Wenlu, who has taught me a lot about computer vision research. And also I'm glad to meet Huazhi and Yan during my visiting years at Berkeley, who is now also doing a faculty position in Tsinghua University. So I'm also fortunate to work at multiple internships during my PhD study. Actually, I go out for internship every year, every summer. So I've been working at OmniML, which is a startup that we built with Professor Sung Han, and later get acquired by NVIDIA. So I also did a year internship at NVIDIA this summer. So I met a lot of wonderful persons, including Huizi, Di, Danny, Wei, Andrew, Mohammed, Pablo, Yang, Julian, and Mikhail. So they helped me a lot in various dimensions, and also we work closely on some of the projects, for example, like SmoothQuant and AWQ, and help push these techniques into the applications. And I also had a really great time at Adobe Research during my year in 2020. So I worked with Richard, Junior, and Frieder, Ali, and Selvian. So we have been keeping in touch ever since, and they also helped me a lot during my job search this year. So I would like to take this moment to express my gratitude to my mom and dad. So due to like different reasons, I have not been able to meet them for almost 4 years. So I've not been back to China for a very long time, like after COVID. But they have been consistently providing the support remotely. So they actually know nothing about research, especially in computer science, but they have been trying hard to provide the best for me to grow up. So I could not have achieved anything without their unconditional love and support. So I hope I can make them a bit proud at the end of the day. So finally, I would like to extend my gratitude to my wife, who is also here today. So I think I'm very lucky to meet a woman who completes me. So we have been going through various ups and downs over the years, and I could not have made it through without her love and company. And for another interesting is that we have a dog named Soda. So she is also supporting me all the way around my research. So that concludes my talk. Thank you. Thanks everyone for attending.